All right, everybody, welcome back here. This is the last lesson of Chapter 7, Applications of Exponential and Logarithmic Equations. Okay, just a quick summary here. We saw the continuous compounded interest formula. Okay, that also works for any continuous growth decay situation. Again, the only thing that's different, P e to the RT, here it's C e to the KT again. C is the initial value, just like your principal. K is your growth, and instead of your rate, same thing, stands for the rate. And if it's decaying, it's negative. And then your time is your time. So PE to the RT, very similar situation, except now we could potentially have decay. All right, so you just make your power negative. If it's losing 5, it'd be negative 0.05. Okay? Don't worry about that. Here's all your other formulas. Okay, and again, we can see that these two are very similar. One is just money, compound interest, so your rate is always going to be positive. If your rate is negative for your continuous growth decay situation down here, okay, we just have to remember that this is a negative number and this is a positive number, your percent as a decimal. Okay, so let's get into it. Just summarizing here. Any possible situation we could see, and we'll go from there. Okay, so a population of Amazonian monkeys has been declining at a continuous rate. Okay, declining, continuous rate. How many monkeys will exist in 4 years if there's 20,000 monkeys today? So, initial value is 20,000. Okay, E, because it's continuous, and our rate is 5%, but we're losing 5% raised to the 4 years. All right, so we jam that in our calculator. Okay, pull this up. Okay, that means we'll have 16,374 monkeys after 4 years if they continuously decrease at that specific rate. All right. Okay. So that's just an example of a continuous decrease where your rate has to be negative. All right. The next one, population of monkeys has been declining at a continuous rate of 5%. In how many years will the population decrease to 5,000 if there are 20,000 today? So our starting value is 20,000, e to the negative 0.05. We don't know the time, okay, but I want to know when, how long does it take to get to 5,000? All right, so we're going to divide both sides by 20,000. Okay. Okay, so your first step is undoing that multiplication. So we have e to the negative 0.05t equals 0.25. All right. Now to undo base e, we have to use the natural logarithm. All right. So we're going to take the natural log of both sides. Okay, and remember when we do that, our exponent becomes the coefficient. Natural log undoes the e. And then we divide by negative 0.05. So we do the natural log of 0.25 divided by negative 0.05, and we get 27.7 years. Okay. All right, so same idea, the decreasing rate, making sure your rate is negative, and undoing e with the natural log, and dealing with that exponent as a coefficient now. Okay, pretty straightforward. All right, the rest is just a review of everything that we've kind of gone over already. All right, so a 100 milligram sample of radioactive substance has a half-life. Okay, so details here. Half-life of every 30 minutes. How much of the substance remains after 3 hours and 15 minutes? So initial value is 100 milligrams. Okay, multiplier is a half or 0.5. Okay, and our function is going to be how much time over every 30 minutes. So because our time here is in minutes, I have to convert 3 hours and 15 minutes to total minutes. Okay, so 3 hours times 60, that's 180 plus 15, 195 minutes. All right, so we're substituting 195 back in for our total time. All right, so we just plug and chug here. Which means 1.10485 milligrams remains of your radioactive substance. Same situation, 100 milligrams, half-life of 30 minutes. After how long will 20 milligrams remain? Okay, so our original function we had above. All right, so how long does it take for 20 milligrams to be left? So we're going to substitute 20 in for y. So first step, to get x by itself, we're going to divide by this 100. So we got 0.2 equals 0.5 raised to the x over 30 power. And then we take the log of both sides. Okay, a couple different ways to do this. As shown in the previous 7.5 solving logarithmic equations, I'm just showing you one way. Okay, so we have log of 0.2 equals x over 30 log of 0.5. All right, so to get to that x, we can divide by this log, 0.5. Okay, I'm going to leave it exact because I do not want to use a rounded answer. Okay, and then I can just multiply both sides by 30 to get that to drop. So in your calculator, you can take 30 times the log of 0.2 close that off, divided by the log of 0.5. And we get 69.658 minutes. Okay. All right. Last question here. Okay, this is a good one here. If someone has some money or you have an inheritance or anything like that, maybe your parents set something up like this for you guys that you don't even know about. One can only hope, right? Okay, so Johnny's grandparents put 10 grand into an account when he was born. On Johnny's 18th birthday, his grandparents gave him $26,851.54 to use towards college or whatever. Assuming the interest was compounded monthly, what was the interest rate for the account? Okay, now it says here use a graphing calculator to solve. I'm going to show you algebraically and then show you how to confirm that graphically. All right, and again, it's nice to show that everything checks out. So let's see here. Let's build our compound interest formula based on monthly, it being compounded monthly. So you have $10,000. 1 plus, we don't know the rate, over 12 months times 12 months times 18 years. All right? And that outcome is $26,851.54. Our job is to solve for that x right there. All right, so let's undo this thing. So we're going to divide by 10,000. Okay, and this is 12 times 18 is 216. I'm going to leave this exact once again. Okay, well actually I can divide that. Okay, it's just 2.6855154. Okay, move that decimal 1, 2, 3, 4 times. 1, 2, 3, 4 times. Okay, by dividing by 10,000. And then to undo the 216th power, we can take the 216th root. Okay, so we take the 216th root of both sides, which leaves us 1 plus x over 12 equals, let's see here, 216 math 5 of 2.6855154. All right, so we get that. 1.004583 forever. All right. Continuing to solve for this x, we subtract 1 from that. Okay. And then last step, we multiply by 12 to undo divide by 12. So we take that answer, multiply it by 12, and we get a rate of 12. Oops, I forgot to subtract 1. Okay, so we take that answer, subtract 1 from it, then multiply by 12. Okay, we get 0.054999999 forever, which we're going to round that to 0.055, which means to find the interest rate, move this 1, 2, it's 5.5% interest compounded monthly. On the graphing calculator, what we would do is simply set this left side of our equation as y1, the right side of the equation as y2, and then we find the x value, the x coordinate of the point of intersection, and it should be the decimal 0.055. Let's see. So let's go here and clear out whatever's in there. 10,000. Times 1 plus x over 12 raised to the 216th power, and I want that to equal $26,851.54. Okay, so when I hit graph, okay, I need to go way high, right, to find 26,000. Okay, so I could even squeeze this over here. I know it's going to be a very small number. Okay. So I'm looking for this point of intersection. As I track that down, boom. The x value is 0.054999999, which is your 0.055 interest rate. Okay, so that's what you guys should be doing for all these questions. A quick check, especially on an assessment. Doesn't hurt to jam it in your calculator and just confirm everything. Again, the calculator is used to check, not as your sole method of finding. Now that we know how to use logs and how to undo and how to solve, we didn't even use logs for this one. We actually used inverse operation of the 216th power, which is the 216th root. Okay, and then simple algebra from there on. Okay, but again, try and keep that long decimal in there. I just kept reusing that answer on my calculator because the moment we round that, we're not going to get an accurate rate. Okay, we want to keep all those decimals in there. Okay, so continue working with this. Continue applying your properties of logs. Again, I know, in class we discussed different ways, whether you use the natural log of both sides, or whether you take the log of both sides, or whether you take, the base and then do the change of base formula. They're all equivalent paths to the correct answer. Okay, so as long as you're not breaking any mathematical rules, you are fine. The path we get there, however, can be different from person to person. But in the end, we can always confirm, just like I did on the calculator here, type in the left side is y1, the right side is y2, and find the x coordinate of the point intersection. So continue practicing these applications, continue asking questions and clarity if you need that. And we're going to wrap this chapter up, and when we come back from Thanksgiving break, we'll review and we'll test on it. Okay, guys, great job.